Welcome to this video on frequency measures, where we explore how to summarize, visualize, and compare clinical data. As John Maynard Keynes once noted, it is better to barely right than precisely wrong. Healthcare generates vast amounts of data daily. Because looking at raw data is overwhelming, we use frequency distributions to compress that mess into a meaningful story. A frequency distribution shows the values a variable can take and how many observations are associated with each. An ungrouped frequency distribution lists every distinct value alongside its count. This is especially useful when your variable has only a small number of possible outcomes. Visualizing this as a histogram helps identify trends, like the modal length of stay seen here. When data spans a wide range, we use grouped frequency distributions. By organizing values into non-overlapping class intervals, we can clearly see the overall shape of the distribution, such as this bell-shaped pattern showing that short or very long stays are uncommon. Before we dive deeper, what is a variable? Simply put, it is any property or characteristic that can take on different values across patients. That inherent variability is exactly what statistics aims to study. Variables fall into two main families, quantitative and qualitative. A simple test. If you can calculate an average for the values, it is quantitative. If not, it is qualitative, representing categories or qualities instead. Quantitative variables are further split into discrete or continuous types. Discrete variables, like counting hospital beds, are defined by integers with gaps between values. Continuous variables, like body weight, are measured and can take any value within a range. Now let's look at the scales of measurement, starting with the nominal scale. Here, we only categorize and count. There is no inherent order, so you cannot rank things as better or worse. Next is the ordinal scale. Observations are still classified and counted, but now they possess a meaningful order. A common example is a Likert scale, where we know one response is more positive than another, even if the spacing between them isn't perfectly equal. The interval scale features equal intervals between values, but lacks a true 0 point. This means while we can rank differences, ratios are not meaningful. Examples include temperature in Fahrenheit or calendar years. Finally, the ratio scale is the highest level of measurement. It includes all the properties of the interval scale, plus a true, absolute 0 point. This allows for meaningful ratios, which is why most physical measurements in healthcare belong to this scale. Now, how do we find the typical value? We use measures of central tendency to determine where the data tends to cluster. There are three primary measures: the mode, the median, and the mean. Each captures the typical value differently and is appropriate for specific scales of measurement. The mode is the most frequently occurring value or category. It is the only measure appropriate for nominal data, like blood types, where you cannot mathematically average the categories. Finally, the median is the middle position when data is ordered. It is the midpoint of the distribution and is particularly useful when you have outliers, as it is not as easily distorted as the mean. To calculate the median, we first find the middle position. For 75 student ratings, we use the formula n+1 divided by 2, which gives us the 38th case. Looking at the cumulative frequencies, we can see that this case falls within the moderate rating, making it the median. Next, we have the mean, or arithmetic average. You add all values and divide by the total count. It serves as the balance point of a distribution and is fundamental to further statistics. However, it requires interval or ratio data and is sensitive to extreme values or outliers. When dealing with data of different sizes, a simple mean can be misleading. In these cases, we use a weighted mean. As shown in this example, aggregating across months using the total length of stay ensures that our average remains accurate, even when discharge volumes differ. Moving to measures of variability, the range is the simplest to calculate, the maximum minus the minimum. While quick to find, it can be misleading, as two very different distributions can have the exact same range. Variance measures how far data points spread from the mean. We compute it by finding the average of the squared deviations. Using Bessel's correction, or n-1, ensures our estimate is unbiased for samples. Since variance uses squared units, we take its square root to return to the original scale. This gives us the standard deviation. For normal data, the empirical rule tells us that most observations fall within 1, 2, or 3 standard deviations of the mean. Let's apply the empirical rule. If nursing home ages are normally distributed with a mean of 82 and a standard deviation of 4.45, roughly 68% of residents fall within one standard deviation. This gives us a range of approximately 77.6 to 86.5 years. Percentiles identify a value's position relative to the whole dataset. They tell you where a specific observation ranks. Common quartiles include the 25th, 55th, and 75th percentiles, which divide the data into manageable segments for easier analysis. Moving to ratios, we compare two distinct quantities. Crucially, the numerator is not part of the denominator. For example, comparing female to male births, a ratio of 1.16 shows there were roughly 116 girls for every 100 boys. In contrast, a proportion includes the numerator as part of the whole denominator. Proportions are always expressed as values between 0 and 1, or as percentages. Here, we see that female births account for 54% of the total. A rate is a proportion measured over a specific time period. We multiply it by a base factor, like 100, to make comparison easier. For example, a 15.4% C-section rate provides a clear metric for hospital quality. Hospital statistics are the daily metrics that keep a facility running. These include census, occupancy, turnover, and length of stay, each serving as a pulse check on operational performance. The inpatient census is the number of patients present at a specific time, usually midnight. This daily count is vital for resource allocation. By adding admits, subtracting discharges, and accounting for same-day patients, we maintain an accurate record of daily occupancy. The occupancy rate tells us what portion of available beds are filled. We calculate this by dividing patient days by total capacity. Whether looking at daily or weekly trends, this rate is essential for understanding how well we utilize our resources. Finally, the bed turnover rate shows how quickly beds are cycled for new patients. By dividing total monthly discharges by the average bed count, we can determine the intensity of bed usage, which is key for efficient capacity planning. Length of stay, or loss, is calculated by subtracting the admission date from the discharge date. Conventions for counting days vary, but typically include the admission day. In this example, the patient was admitted May 12th and discharged May 17th. With a total stay of 27 days across 5 patients, the average loss is 5.4 days. The hospital mortality rate represents the proportion of inpatients who die during their stay. It is calculated by dividing total inpatient deaths by total discharges, including deaths, then multiplied by a constant. Variants like gross, net, and postoperative mortality provide more specific insights into hospital performance. We now move to morbidity and safety. These measures are crucial for understanding disease occurrence and ensuring patient safety, involving everything from tracking infection rates to performing risk-adjusted comparisons. Morbidity is measured through incidence and prevalence. Incidence counts newly diagnosed cases over an interval, helping us study causes. Prevalence counts all existing cases at a point in time, helping us understand the overall burden of a disease. Let's apply these measures to a nursing home audit. With 10 new cases and 7 pre-existing cases among 250 residents, the incidence rate is 4% per year, while the point prevalence is 6.8%. Nosocomial infections develop at least 48 hours after admission. By comparing the nosocomial infection rate and postoperative infection rate, we can pinpoint safety issues. Remember, the denominator is key. Failing to adjust for patients at risk can lead to misleading comparisons between wards. Overall infection rates can obscure the truth. Stratifying by risk categories, such as wound class, is a powerful way to identify where the real problems are occurring within a clinical setting. Subgrouping is equally important for tracking medication errors. Rather than just reporting a general error rate, breaking errors down by type, such as wrong dose errors, allows teams to implement targeted, actionable interventions. A measure is only as good as the quality of the data behind it. To be useful, every clinical measure must be evaluated for validity, reliability, sensitivity, and specificity. Validity asks if we are measuring the right thing. Reliability checks for consistency across repeated tests. Sensitivity determines if we catch every case of the condition, and specificity ensures we correctly rule out those who are healthy. Validity can be tricky when we cannot observe a concept directly. We use proxy measures to track it. For example, we track diabetic inpatient admissions as a proxy for the effectiveness of community-based ambulatory care. Reliability is about consistency. If a measurement is reliable, it yields the same results time after time. However, remember the target analogy. A measurement can be perfectly reliable and consistently wrong, meaning it lacks validity. Sensitivity and specificity are derived from a 2x2 table. Sensitivity identifies true positives, while specificity identifies true negatives. Generally, you want a sensitive test to screen for potential cases and a specific test to confirm them. In practice, like with hepatitis C testing, we pair a high-sensitivity screen to catch all potentially infected patients with a high-specificity confirmatory test to rule out false positives. This two-stage process ensures accurate results. To summarize, master your frequency distributions, respect your measurement scales, and always pair your central tendency metrics with a measure of variability. Most importantly, remember that validity, reliability, and precision are the bedrocks of meaningful clinical data.